Welcome back to our lecture. Let's then briefly recall what we did the last time. So, in the end of our last lecture, we started with quantifying classical information. In particular, let me recall that we again highlighted that classical information can be associated with a random variable. Okay, so say we have a random variable capital X, and this has some outcomes, say A1 to AN, which appear with probability P1 to Pn. And the typical scenery that we had in mind was a communication protocol between Alice and Bob. That Alice sends a message to Bob using this alphabet, where these letters, which we also call symbols, appear with these probabilities P. And we then, by this, we then have seen that the information can be reduced to this transition to this probability distribution, right? And we quantified the information by the Shannon entropy. In particular, the Shannon entropy tells us the uncertainty of Bob before he learns the outcome of this random variable. Okay, so suppose that Alice sends so she draws one symbol from this random variable, sends it to Bob, and he then learns it. And once he learned the outcome of this random variable, he gained the information, and how much of information he gained was quantified by this Shannon entropy, right? And the Shannon entropy was defined as h of x being minus the sum over all outcomes x with probabilities px, and then we had the logarithm to basis 2 of px. And in an example that we did, we've also seen that the Shannon entropy also quantifies the physical resources which are required in order to store this information. And by physical resources, I mean the number of qubits per symbol source, the number of qubits per source symbol, which are needed in average to save the message of Alice, right? So meaning that take one of these symbols, and then on average, the Shannon entropy tells us how much bits do we need in order to save this information that we gain if you learn the outcome of this random variable. And we did an example with different encodings, right? This example had 4 symbols, and we took a look at 2 different encodings. One was a very naive encoding, where we encoded the symbols in 2 bits, right? Meaning on average if we have k symbols, on average we had to send 2 times k bits from Alice to Bob. But then we came up with a more intelligent encoding. So, and the way how we did this is we encoded those symbols which appear with very high probability in symbols which only need very little bits, right? And those symbols which appear with small probability, those were encoded in symbols which had longer, which were associated with a longer bit chain, right? And then we've seen that on average, we can go below this number of 2 times k bits. And the minimal number in which we can encode then a symbol on average is quantified by the Shannon entropy, right? Meaning that it tells us a number, it tells us how good can we compress this classical information. Okay, and so this is just a recall what we did the last time. What we're gonna do next is we're gonna study relations between 2 random variables. So we stay at the level of classical probability distributions, still everything is classical, and now we say, okay, we have 2 random variables, and we ask how are they related to each other. And the first, so this is then the chapter of further classical entropies, so section 3.3.2. And the first thing that we want to study is very similar to the trace distance between classical probability distributions, right? What we want to do is we want to come up now with a measure which tells us how distant are two classical probability distributions, now with a measure which is related to the Shannon entropy. And this is the so-called relative entropy. So, and this is defined as follows. This is definition 3.7. So, given two probability distributions, let's call them P and Q, over the same index set, then the relative entropy of P to Q is defined as follows. So we write this as H and then P relative to Q is also written as Px relative to Qx, and this is the sum over x, and then we have Px times the logarithm of Px over Qx, and this is minus the Shannon entropy. So if you take a look at the definition, so we have minus the Shannon entropy of x, and then we have minus sum over x Px logarithm of Qx. So this is equation 121. And now you might wonder, why do we again want to have a distance measure? Because we already have the trace distance, right? And you also might wonder, is this actually a distance measure or not? Because it's not obvious from this definition, right? And in order to see that this measures a distance of P relative to Q, let's state the following theorem, from which we then see that this is a distance measure. So that's theorem 3.12, and it says that the relative entropy is non-negative. So the theorem is called non-negativity. Of the relative entropy. It's as follows. So simply says that the relative entropy is non-negative, meaning that the relative entropy of P to Q is greater or equal to 0 with equality if and only if let me write this now in the other notation, namely as Px Qx. So with the equality, if and only if Px is equal to Qx for all x. And with this, we see that, okay, indeed we can see this as a distance measure, right? Because it's always greater or equal to 0, and with equality if those probability distributions are equal. Well, we're now going to prove it, and then I'm going to say some more words to this. So let's prove it. And for the proof, consider the following. So consider that suppose set, so we write simply a number set as 2 to the power of the logarithm of set. Okay, so we did, meaning set is equal to set, because the logarithm is always taking to base 2. And now let's take the logarithm to base e on both sides. So it's ln of set is then equal to ln of 2 to the power of logarithm of set. And then this can be written as the logarithm of set times ln2. Okay, and now we're going to use the following. So now we use that the ln of set is greater or equal to set minus 1 with equality if and only if set is equal to 1. Okay, so we can use this here. So what we then find is that the logarithm of set is equal to ln of set over ln of 2, and this one is now greater or equal to set minus 1 divided by ln of 2. Then using this in equation 121 with set equal to qx over px, we get the following. So we get that the relative entropy of P relative to Q is equal to, okay, now take a look here at this expression. So first we take out the minus sign and write and take the inverse of the argument of this logarithm. So actually we have qx over px. Okay. And next we now say, okay, this qx over px is set. And we use this inequality here because we then have here logarithm of set. Right? So we see this is greater or equal to that, meaning sorry, there's a mistake. This must be smaller equal. Right, and then this must be smaller equal. Sorry for that. So because now since we have a minus sign here, if we use this, we get a greater or equal sign to minus sum over x and then px times the logarithm of and then sorry, px times qx over px minus 1 divided by ln2. Okay, so this is minus 1 over ln of 2 and then sum over x. Then we have qx minus px. Okay, and the next thing we recognize is that these are probabilities forming a probability distribution. So we get minus 1 over ln of 2 and then 1 minus 1, which is 0. Okay. And with equality, if and only if qx over px is equal to 1, right? Meaning that Qx is equal to Px. If and only if Qx over Px equals 1. Well, this finishes the proof. Okay, so now, as I already mentioned, let me say some words to the relative entropy. So, the first thing that we possibly recognize by its definition is that it is not symmetric. Okay, and it also does not satisfy the triangular inequality. And with this, we directly see that the relative entropy is not a metric on the state space of probability distributions, right? Because you possibly remember the trace distance. For the trace distance, we know that it is a metric because it satisfies all the requirements for a metric. So being symmetric, positive, satisfying the triangular inequality, and being zero if and only if the probability distributions are equal. So those are the requirements for being a metric. And the relative entropy does not satisfy all these requirements. However, it's non-negative, and by this we can associate it with a measure of how distant is P from Q. Okay, so the relative entropy is not a metric on the space of probability distributions since it doesn't or since it is not symmetric. It is not symmetric and doesn't satisfy the triangular inequality. Okay, so you possibly also wonder, okay, why do we introduce it then? So as I said, the reason why we do it is because it is related to the Shannon entropy. Okay, and this you can see directly by its definition, because on the right-hand side we have the Shannon entropy there, right? And by this fact, it is useful because we want to study the Shannon entropy, and as I told you, we also want to study the Shannon entropy between two different random variables. Well, and what we're going to do next is we're going to use this relative entropy and show one property of the Shannon entropy that I implicitly stated several times so far. Okay, so remember when we started this section on quantifying classical information, we had in mind this communication protocol between Alice and Bob, and when we encountered the fact that classical information can be associated with the probability distribution, we did this example that we considered different probabilities with which Alice chooses those symbols and sends it to Bob. And in particular, we've seen that if all those, or we stated that if all those symbols appear with the same probability, then Bob is maximally uncertain about the message of Alice. Okay? Meaning that the information content of this message is maximal. That's what we stated. And this is exactly what we're going to prove now. So now we do a formal proof of this statement that the Shannon entropy is maximal if we have a uniform probability distribution. Okay? So this is our next theorem. So theorem 3.13. Which is the maximum of the Shannon entropy. So it's as follows. So for x, a random variable, with n outcomes, the Shannon entropy satisfies that h of x is smaller or equal to the logarithm of n with equality if and only if x is uniformly distributed over those n outcomes. So it now states the upper bound of the Shannon entropy. And it also states that it is only reached, so it's reached if and only if x, so the random variable, of course, gives rise to this uniform probability distribution. And this is, this is intuitive, because remember, we used this, we used this result to kind of come up with a reasonable interpretation of classical information. So let me state this. Let me prove this theorem. Well, as I already said, we're going to use now this the relative entropy. So I just erase it now, but I think you have it in front of yourself, the manuscript. And what we do is, well, the idea is simple. We take a look at the relative entropy between a probability distribution and the uniform probability distribution. So the proof is as follows. So consider the relative entropy between, or let's say of P, the probability distribution P, to the uniform distribution Q, so where all the probabilities are 1 over n. So let's consider this. So we have h of px relative to qx equals minus h of x. Okay, so this is the probability distribution P is associated with the random variable x, right? And this with the random variable y, just as we've had it before. So we have this, and then minus sum over x, px logarithm of qx. So this is how we stated it in the definition. So let's plug here now for qx, we can plug in 1 over n, right? So we have minus the logarithm of 1 over n and then sum over x px. But then we know that this is 1. And then we have minus h of x plus the logarithm of n. Okay, now we use the non-negativity of the relative entropy, which we just proved. So we know that this is greater or equal to 0. Hence, or let's say with equality, we have to state fact, with equality, if and only if the probability distribution P is equal to Q. Hence, we have h of x greater or equal as smaller or equal smaller or equal to logarithm of n with equality if and only if P is equal to Q. Okay, which finishes the proof. So again, what we did is we took a look at the relative entropy between the probability distribution P, which corresponds to the random variable x, and the uniform probability distributions where all the probabilities are equal. We took the definition of this relative entropy, plugged this in. For Qx, we get 1 over n because it's a uniform distribution. So we can put this out of the sum. Then we are summing over probabilities from a probability distribution, gives 1. And then we used here in this last step the non-negativity, which we just proved. And since we know that the non-negativity, that there we have equality if and only if this probability distributions which we compare are equal, we know that the Shannon entropy must be smaller or equal to this constant here, to log n, with equality if and only if it's the uniform probability distribution. Okay, so this proved this statement that we intuitively used before several times. Now we have a formal proof. And I'd like to continue now with some relations between two random variables. Okay, with some further relations. And to this, suppose that we have now two random variables, say x and y. And suppose now that first we're going to learn the outcome of y. And then based on this outcome, we learn the outcome of x. And suppose that these two random variables are not necessarily independent, so they can be correlated. Okay? And in order to get a impression how we can illustrate this, let me do a small example. Suppose that those random variables x and y have two outcomes. Okay? And let me now draw the tree diagram. So I'd like to recap a little bit from probability theory, what you already learned so far. So let's suppose that we start here with our tree diagram, and first we have the random variable y, okay, and this has the outcome. Let's say here. So it's random variable y, which has the outcome either 0 or 1. And then we have the random variable x with outcome a or b. Okay, so let's now draw this tree diagram. So first, we learn the outcome of the random variable y, meaning that we get 0 with probability p of 0, and we get 1 with probability p of 1. Okay, so what we are dealing with here are the probabilities p of y. Okay, and now, as I told you, that these random variables are possibly correlated. Okay, meaning if we now learn the outcome of the second variable, okay, then we get a with the probability to get a under the condition that we get 0 before. So this is the so-called conditional probability. It tells me what is the probability that the random variable x yields a if the random variable y gave us 0. Okay? And here then is the probability that we get b for the random variable x, and we get 0 for the random variable y. Okay, so we end up here with b. And similar here, we have the probability that we get a conditioned that the random variable y gave us 1, and here's the probability of b conditioned on 0. Okay, so meaning that here we're dealing with conditional probabilities p of x conditioned on y. Okay, and what do we get out here? We get this this branch here of the streak diagram comes with the probability p that x gives a and that y gives 0. Okay, and here's the probability that x gives b and y gives 0, and this is the probability p that x gives a and y gives 1, and here's the probability p that x gives b and y gives 1. So these are the so-called joint probabilities p, x, y. Okay. Okay, let me write this down. So, so here p x y, which is equal to p of y times p of x under the condition of y, is the joint probability. And p of x under the condition of y is the conditional probability. Okay, so it's the joint probability that the outcome x gives x, and the random variable capital X gives the outcome x, and the random variable capital Y gives the outcome y. Okay, and this is the conditional probability that the random variable capital X gives x under the condition that the random variable capital Y gave y. Okay, and please keep in mind this tree diagram, and I wanted to refresh those probabilities and how they're called, because we're now going to see very similar expressions for entropies. Okay. So the first thing that we want to do is we want to quantify how much information we gain if we learn both random variables, x and y. Okay, that's the next thing that we do. So keep in mind, suppose you have two random variables, x and y, and they can be possibly correlated to each other, right? Meaning that they are not necessarily independent. And what we want to do now is we want to quantify how much information we gain if we learn both random variables. And for this, simply take a look at this tree diagram and consider which probabilities there are in the case of learning both random variables. Well, if I learn both, then this kind of must be related to those joint probabilities, right? Because those joint probabilities we get if we learn both. And well, with these joint probabilities, we now get the so-called joint entropy. Okay, so joint entropy, and it's defined as follows. So it's definition 3.8. the joint probability, the joint entropy, sorry, of two random variables x and y is defined as follows. So we denote it by h of x, y, and this is minus the sum over all x and y of pxy times the logarithm of pxy. And you see that the joint entropy is simply the Shannon entropy of the joint probabilities. Okay? So as an input, we now have the joint probabilities p, x, y, and we simply calculate the Shannon entropy. So the joint entropy is the Shannon entropy of the joint probabilities p of x, y of x and y. So what does it now quantify? Well, as we wanted it, it quantifies now how much information we gain if we learn the outcome of both random variables. Right? That's what it does. Let's write this also down. So it quantifies the amount of information which we gain if we learn the outcome of the pair x, y. Okay, now let us do an interesting, let us consider an interesting case, namely the case where those random variables are independent. Okay, so for independent random variables, x and y, we have that the joint probabilities are simply a product of px times py. So you see that they're independent because the probability that if we first learn the outcome of y and then the outcome of x, then the outcome of x does not depend on y. Okay, it's because they're statistically independent. And in this case, we get that the joint entropy of x and y is simply the entropy of x plus the entropy of y. Okay, it tells us, okay, if we learn both outcomes, then the information we gain is the information we gain if we learn x separately and information if we learn y separately. Right? However, if now they are correlated, then suppose we first learn y because we first learn the outcome of y, and if they are correlated, then the outcome of y can give us already some information what x will be. Okay, And this means then that the joint entropy will be smaller than this plus this. Okay? So if x and y are correlated, then the joint entropy must be smaller than h of x plus h of y. Because if we learn y, then we already have some partial information about the outcome of x. This is the correlations, right? And suppose now that, I think I'm going to state this before the break. So suppose now that we do have these two random variables, and first we learn the outcome of y, and then we can ask, okay, how much information do we gain if we now learn the outcome of x, given that we know the outcome of y? Okay? So how much do we learn more? Well, this gives then rise to the so-called conditional entropy. And the conditional entropy is defined as follows. It's definition 3.9. Namely, for a pair of random variables, so the pair xy, the entropy of x conditioned on knowing y or conditioned on knowing the outcome of y defines the conditional entropy which is h of x conditioned on the y equal to h of x y minus h of y. Okay, this fits perfectly in this picture that we had. So recall that if we have independent random variables, then the joint entropy is simply the entropy of x plus of y, meaning that the information that we learn if we learn x plus the information that we gain if we learn y. Right? If there are correlations, then we know that the joint entropy must be smaller than the sum, because if we first learn y, then we already have some information about x. Okay, so the joint entropy then must be smaller than this. And this conditional entropy now states, okay, that we have the information that we learn in this case, meaning that if we learned y and now we learn x, is given by the joint entropy minus the entropy that of y, which is the information that we already learned before. Okay. So, and with this, I think it's a good time to do a break. And after the break, we're going to continue here, and we're going to define one more entropy quantifier. Okay. See you after the break. Let's continue. So before the lecture, we learned some further entropic measures, which I just summarized here. So first, it was the joint entropy, given by the Shannon entropy of the joint probabilities. And then we defined the conditional entropy as the joint entropy minus the entropy of y. So this is the meaning this is the information that we gain if we learn the outcome of the random variable x, given that we learned the outcome of y. Okay, so meaning that from this joint entropy, we simply subtract the entropy of y, because we already learned y. Okay? And you see that all these expressions are very similar to the probabilities. Okay? So before, we've seen that this joint probability, for example, okay, is p of x, y. Okay? We had p of x, y is equal to p of y times p of x conditioned on y. And this gives rise to this form, then that p of x conditioned on y is equal now to p of x, y divided by p of y. Okay? And it's exactly this form here. However, instead of dividing, what we do here is we subtract. And the reason for this is the logarithm in the definition of the Shannon entropy. Right? Because of this logarithm appearing here, we get this minus sign. Okay? Otherwise, it has the very same form. This is how you can really how you can see the analogy between those things, right? Because I'm sure that you know those things, and this is nothing new, right? This is just now a quantifier of information, and it kind of follows from these things here, and that's why they take the very same form. But due to the logarithm, we now here add or subtract instead of multiply or divide. Okay, so at the end of the first part, we ended up here with the conditional entropy. Okay, let's now take a closer look here. So first, investigate this conditional entropy in the case of independent random variables. Okay, if x and y are statistically independent, then we've seen that the joint entropy is simply given by the sum of their individual entropies, right? And for this conditional entropy, this means that, so for, or if x and y are independent, then the conditional entropy, h of x conditioned on y, is simply h of x, right? So we learn, so this then gets maximal, right? Meaning that since they're independent, this right thing here is also independent on y. And learning, it doesn't matter that we learned the outcome of y before because they're independent. So by learning x, we get the information h of x. If they're correlated, then it's different, right? So however, if knowing the outcome of y, we reveal some information about the outcome of x, then we have that h of x conditioned on y must be smaller than h of x. Okay, this you get if you simply plug in this thing here. And what does it mean? Actually, in other words, it means that x and y, they possess some mutual information. Well, if they're correlated, right, then once I learned the outcome of y, this gives me some information about the outcome of x, meaning that x and y do have some mutual information. And we can now quantify this mutual information. It's our next measure, the so-called mutual information. It's defined as follows. Definition 3.10. The mutual information of a pair of random variables x and y is defined as h of x, y being h of x minus, so plus h of y minus the joint entropy. So this is 3.126. So you see that the mutual information is now given by the information of x itself and y itself minus their joint entropy. Okay? And remember that if we have independent random variables, then h of x, y is equal to h of x plus h of y, right? And then we see that we have zero mutual information. However, if there are correlations, right, then this thing here is smaller than h of x plus h of y. Okay, plugging this in here, we see that we have some positive mutual information. So this indeed quantifies their mutual information, so the information they have in common. So the mutual information quantifies the amount of information which x and y have in common. So for independent random variables x and y, it yields 0, and if x and y are correlated, we have that the mutual information is greater than 0. Okay, now let me do an example. Okay, let's do an example. So suppose that my socks are covered by my trousers, okay, which is the case today. And suppose I also tell you that I always wear socks with different color, namely one bright and one dark sock. Okay, but you can't see now which one is bright and which one is dark because it's covered, right? So this is the example. suppose now this is the left sock, and this is the right sock, and we can now associate a random variable to the color of these socks. Okay, say the left sock is the random variable x, and the right sock the random variable y. Okay, and x can have now the outcomes 0 or 1, and y can also have the outcomes 0 or 1. Okay, where we associate 0 with the dark sock and 1 with the bright sock. Okay, so remember that I told you that I always wear one dark and one bright sock, and I choose randomly which sock is dark and which is bright. So I choose randomly whether the left sock is dark or the right sock is bright, or vice versa. Okay? So this means that we can now, let's now do as follows. Suppose that, what are the probabilities? Say we are only concentrating now on the left sock. Okay? Let's now figure out the probability that the left sock is dark. Okay? So P of x, so P of 0, P of x equals 0. Well, this is 1/2. Okay? Because I randomly choose to wear the dark sock either left or right. Okay? And then the probability that the left sock is bright is also 1/2. Okay? And from this we can now calculate the Shannon entropy of this random variable, h of x, which is minus 1/2 times the logarithm of 1/2 minus 1/2 logarithm of 1/2, which is 1. Okay? Meaning that if I would now lift, say, the left leg of my trousers, you would see the color and you would gain 1 bit of information. This is what it tells you. Okay? Now similar for the right sock, we have that P of y equals 0 is 1/2, and P of y equals 1 is also 1/2, and the entropy, Shannon entropy of this random variable y is 1. Okay. But now these two random variables, they are not independent. The reason is that I told you that one of them is dark and the other one is bright. Right? So this means that the conditional entropy that, the conditional probability that x is equal to 0 conditioned on y equals 0 is 0, right? Because there are never two socks with the same color. And the same applies if x is equal to 1 and y is equal to 1. However, if x is equal to 1 conditioned on y equal to x is equal to 0 conditioned on y equals to 1, this probability is 1, right? Because we know whenever y, which is the right sock, whenever this one is bright, we are sure that the left one is dark, and vice versa. Okay, so P of x equals 1 conditioned on y equals 0 is also 1. Okay, and now with these probabilities, we can also calculate the joint probabilities. So namely P of x equals 0 and y equals 0, which is the probability P of y equals 0 times the probability P of x equals 0 conditioned on y equals 0. Well, this is 0. And then we have the probability P of x equals 0 and y equals 1, which is 1. And P of x equals 1, y equals 0, 1/2. And this is also 1/2. And then P of x equals 1 and y equals 1 is 0. Okay, from this we can So I simply plugged in these probabilities and these ones here. Okay. And with this, we can now calculate the joint entropy. Okay. So the joint entropy, using this formula here on top, simply calculate the Shannon entropy of these joint probabilities. Well, and this is again minus 1/2 log 1/2 minus 1/2 and the logarithm of 1/2. Same as we calculated here, so this gives 1. Meaning that if we learn the color of both socks, we gained in total 1 bit information, right? But remember that if we only learn the color of a single sock, we also gained 1 bit of information. And this is because the color of those socks are perfectly correlated. Okay? And from this, we can now also calculate the mutual information. So the mutual information, the definition is here. So it's h of x plus h of y minus their joint entropy. So this is 1 plus 1 minus 1. Okay, so 1 plus 1 minus 1 is also 1. And this tells us that those two random variables have 1 bit of information in common. And since h of x is 1 and h of y is 1, and this is also 1, they have all their information in common. This is what it tells us. And this means that once I lift the left leg of my trouser and you learn the color, you can be sure what the color of the other sock is, right? Because they have all the information in common. Okay, let's see. This one is bright, and then this one is dark. Okay. Okay, these are now perfectly correlated random variables, classical random variables. And do not mix this up with entanglement, right? Entanglement is completely different, and I think we already discussed this in detail before. So this is really only on the basis of some classical probabilities and classical statistics. Okay, so with this, okay, now I'd like to state some properties of these entropic measures. So I think most of them we already encountered. However, we didn't explicitly prove them. But for consistency, I'd like to state them. And some of these properties are really intuitive. And the proof of them then remains as an exercise. So I'm going to state those properties in terms of a theorem. So it's theorem 3.14. So for two random variables, x and y, the following holds. First, we have that the joint entropy is symmetric, and the mutual information is also symmetric. And then the conditional entropy h of x of y under the condition of x is greater or equal to 0, and thus the mutual information of x and y is smaller or equal to the Shannon entropy of y, with equality if and only if y is a function of x. This means that y is a function of x. And this actually means that those two random variables are perfectly correlated. Okay? So if I can express y as a function of x, then they are perfectly correlated. Okay? Meaning that if I know x, I also know y. That's what this tells you. And then the third is that h of x is smaller or equal h of the joint entropy with equality if and only if x is a function of y, or y is a function of x. Okay. And then fourth property is the one that we've seen before as well. So it is smaller equal h of x plus h of y. So the joint entropy is smaller or equal to h of x plus h of y. Now with equality, if and only if x and y are independent. And the last property is that h of y conditioned on x is smaller or equal h of y, and thus the mutual information is greater or equal to 0 with equality if and only if x and y are independent. Well, okay, these are all of them. As I told you, okay, we encountered already some of them, and but we didn't formally prove them. And if you go through them and really try to think what this tells you in terms of what kind of information this represents, then they're really intuitive, all of those, right? And that's why I'm not going to show the proof. The proof is an exercise. I can only recommend to go through it, think a little bit about it, that it makes sense. Okay, go through all of the list and try to think why does it make sense. And the reason that we stated here is because we're going to use some of these properties later on. Okay, with this, we are now finished with considering the Shannon entropy and other entropies of classical states or of classical information. And what we're going to do next is we're going to continue with quantum states. So what our aim now is we want to generalize this concept of the Shannon entropy to also account for quantum states. Right? So far the Shannon entropy only holds or is defined in terms of classical information, meaning probability distributions. And since we are here to study quantum information, we want to lift now the concept to quantum states. And this can be done now by the so-called von Neumann entropy, which we're going to define in a second. So it's our next section. It's the von Neumann entropy. And let me first motivate now this transition. So before, we often spoke about a communication between Alice and Bob, right? So suppose we have here Alice who communicates with Bob, and in this classical communication protocol, we always considered an alphabet which is made out of some symbols or letters, right? And those symbols, they appeared with some probability. Now, suppose that instead of choosing some classical letters, we use quantum states and transform the information through a quantum channel. So, as an alphabet, consider some quantum states described by these density operators ρ1 to ρn, which appear with some probabilities p1 to pn. Okay, so Alice now chooses as letters quantum states and builds a message, sends it through a quantum channel to Bob. Well, if now these quantum states are mutually orthogonal, then we can simply deal this with in terms of the Shannon entropy, so in terms of classical states, right? If you take mutually orthogonal states which remain orthogonal, if we transform them through the quantum channel, then this can simply be understood in terms of a classical communication protocol. However, if we are considering quantum states, then it can happen that quantum states they partially overlap, right? And if they partially overlap in Hilbert space, then Bob cannot with certainty discriminate those states. And we can now ask, for example, okay, how much information does Bob lose because those states mutually overlap? Okay, as a very general example, suppose that in 100 years we're doing quantum cryptography or quantum communication through a network of fibers, okay, for example. Right now what we're doing classical communication through optical fibers. Okay, many cities already have internet running on fibers. Suppose now in 100 years we use this infrastructure, or we build an infrastructure with optical fibers, and we do quantum communication using these fibers. And this means that we're going to send quantum information through these optical fibers, which would be single photons, for example. Okay? And now it can happen that the wave packet with which we describe the single photon, they overlap, okay, in this fiber. And then if we, for example, want to find out what is the capacity of such a single fiber in terms of how much information can be sent through this fiber, then we are exactly in this situation where we have a communication protocol with some quantum states which possibly overlap, right? So this just as an example. Another example that we're going to consider is as follows. So suppose that Alice and Bob share an entangled state, then we can ask, okay, how much mutual information do they have due to this entanglement? Okay? So these are now scenarios that we want to study, and therefore we need a generalization of this Shannon entropy to quantum states. Okay? So here in this case of this communication, what Bob receives is the state, I forgot to tell us, so Bob receives the state rho, which is the sum over j, pj, rho j, okay? Because Alice draws the state rho with probability p. And then this is the state that Bob receives. And, well, what he want to find out is, okay, what letter did he get? Right, and if they are mutually orthogonal, then it's easy for him. right? Because he can find a measurement with which he can perfectly discriminate all the states. However, if they partially overlap, then Bob is to some degree uncertain what the message is. And we are now defining the von Neumann entropy with which we can quantify how much information such a state has. Okay. So we want to generalize the Shannon entropy such that it accounts for quantum states rho and reduces to the Shannon entropy when considering an orthogonal pure states. Okay, so this is just a summary of what I just said, and this can be done by the von Neumann entropy. So this is definition 3.11. The von Neumann entropy of a state rho on H, so on the Hilbert space H, is defined as we call this S of rho. It's minus the trace of rho times the logarithm of rho. Okay, so this is the definition, and it's possibly hard to see that, or it's not obvious how this is related to the Shannon entropy. I mean, it takes very interesting or a very similar form in terms of you have rho log rho, right? But the direct connection to the Shannon entropy gets evident if you put in the eigen decomposition of rho. Okay. So the connection to the Shannon entropy becomes more clear if we insert the eigen decomposition so rho equal to sum over x lambda x and then the eigenstates lambda x into 3.127 with lambda x the eigenvalues with associated eigenvectors lambda x. So let's do this. And the nice thing about the eigendecomposition is, of course, that the eigenstates are mutually orthogonal. So we can easily calculate this trace and also easily calculate the logarithm. So in this case, the logarithm is simply in this basis of the eigenstates given by taking the logarithm of the eigenvalues. So using that the logarithm of rho is equal to sum over x, then the logarithm of these eigenvalues, lambda x, we get that the von Neumann entropy of rho is equal to minus sum over x, and then we have lambda x and logarithm of lambda x. So what you see is that the von Neumann entropy is simply the Shannon entropy of the eigenvalues of rho. Okay? So this is what we get. Hence, the von Neumann entropy is the Shannon entropy of the eigenvalues of rho. Okay, this means that it is the Shannon entropy with respect to the eigenstates. Lambda x. Okay, those are our orthogonal eigenstates. Okay, so this expression here now turns out to be very useful because we already know some properties of the Shannon entropy, and from this we can infer properties of the von Neumann entropy. Okay? And in the following I'm going to state some properties, some of which are trivial, some which possibly need 1 or 2 lines of calculation. And again, the proof of the following theorem is an exercise. And I think I'm going to say some words, okay, and then we kind of already can be sure that almost all of them are true. So let me now state those properties of the von Neumann entropy in terms of this following theorem. So it's theorem 3.15. The basic properties of the von Neumann entropy. So first, the von Neumann entropy is greater or equal to 0 with equality if and only if rho is pure. Means that we can write rho as this form as a pure state. Then the second property is that the Shannon entropy, the von Neumann entropy is smaller or equal to logarithm of n with equality if and only if rho is maximally mixed. This means that rho is the identity divided by n. And then number 3 is that the von Neumann entropy is invariant under unitary transformations. Number 4 is if the composite system AB is pure, then the von Neumann entropy of the reduced states are equal. And then number 5 is if Pj are probabilities. And rho j are quantum states having orthogonal support. Then the von Neumann entropy of this ensemble is the Shannon entropy of those probabilities py plus the sum of py and the von Neumann entropy of rho j. And the last property is that the von Neumann entropy of a tensor product is the sum of the individual von Neumann entropies. Okay, now let me say a few words to this. Okay, the first property, that the von Neumann entropy is greater or equal to 0, directly follows from this expression, right? So we know lambda, the eigenvalues are always positive, and they are smaller or equal to 1, meaning that this is positive and this is negative. And with this minus sign, we have in total something positive. Okay, so this is then greater or equal to 0. Then next, the von Neumann entropy smaller or equal to the logarithm of n. Okay, so we know that from the Shannon entropy, this expression is smaller or equal to a logarithm of n with equality if and only if those lambdas are all equal, meaning 1 over n. And they are all equal if rho is the maximally mixed state. Because for the maximally mixed state, all eigenvalues are 1 over n in this case. So that's what it says here, with equality if and only if it's the maximally mixed state. Because in this case, okay, we can write this as 1 over n. So all those diagonals are 1 over n, meaning that all eigenvalues are 1 over n. Okay, then this is fine. Then the third property, it's invariant under unitary transformations. Well, look at this expression. It only contains eigenvalues. And eigenvalues are invariant under unitary transformations. So The von Neumann entropy is invariant under unitary transformations. So here, this means that S of rho is equal to S of U rho U dagger. Okay, I'm sure that this is how you understood it. And then, if a composite system A, B is pure, okay, if we studied composite quantum systems, then we learned that if we have a pure bipartite state and we trace out one of the systems, then the eigenvalues of this reduced state are equal for system A and for system B. So they have the same eigenvalues. Right, and since the von Neumann entropy only contains the eigenvalues, we know that they must have the same von Neumann entropy, those reduced states. And then the fifth property, okay, this is not trivial. I'd say possibly you need one line of calculation. Well, recall that those rho, or let me stress that this rho j are orthogonal. Well, if they are pure, right, then this term vanishes and we are left with this one, and this is actually makes sense, right? Because if they're those rho are orthogonal, if they are pure, then this would be an eigendecomposition, and then we are left with the Shannon entropy. And what we have to add on top is if they are not pure, namely their individual von Neumann entropy. So it makes sense, but it's not a proof, right? So the proof needs one or two more lines. And then the sixth property, that the tensor product is equal to a sum of these von Neumann entropies. Well, this directly follows if you write rho and sigma in its eigendecomposition, plug this in this definition here, and then one line of calculation, you end up with this result. Okay, so this is quite intuitive. And I think we have to stop here for today because the time is already gone. And we then continue the next time with doing a small example. And then what we do is we're gonna find analogs of those classical entropy measures which we introduced today. So we're gonna find an analog of this, of the joint entropy, and with the aim of finding a definition of mutual information now in terms of quantum states. Okay, this is the aim of our next lecture, and yeah, that's all for today.